Okay, so the last day we discussed, the Noether theorem for fields, for classical fields, and we derived this theorem, and we saw how, under asymmetry transformation, there is a generalized conserved current, which is given by this expression here, J. Something that I didn't say the last day, and that I'm going to say right now, is that this piece here in parentheses has a name, and is actually related. So this guy from here to here is called minus t lambda nu. So it's a tensor, has two indices, lambda and nu, as you can see, and is related t lambda nu with this minus sign is conventional. So it's the opposite combination. So this tensor t lambda nu is known as the energy momentum tensor. Sometimes it's also called the stress energy tensor. Stress energy tensor. Stress. Oops. Stress energy tensor. But I prefer to call it energy momentum tensor because that's what the name suggests, right? That the energy and momentum of the field is inside this tensor somehow, and we'll figure out how the energy and momentum is inside this tensor with an example soon. Okay, all right. So now we're going to see an example. Yeah, before we see an example, yeah, there was this little exercise that we had to do, right? So we had to take the discrete limit of the Noether's theorem of this current here. Okay, and so we had to use this. So let's use this transformation. So the field becomes the variable q. All the dependence on x. The dependence on x becomes the label I, and then the only thing that remains in Q is the time dependence, right? There is no x dependence in Q, so that means that x entirely goes to time, and any derivative with respect to x, of course, has no counterpart, has no analogous object here in the discrete system, because there is no derivative with respect to I, with respect to the index I. Okay, so then if you do this, well, you can already see what is going to happen, right? So your j, so your derivative mu of j mu equals 0, which is, the derivative mu of, let me just write it like this, of partial of L with respect to eta rho comma mu delta eta rho minus delta mu nu times the Lagrangian density minus dl with respect to eta rho comma mu eta rho comma nu delta x nu plus omega mu equals 0, right? So the first thing that we have to do is remember that the Lagrangian is d3x of the Lagrangian density. So therefore, we integrate over dx everything. All this thing equals 0, right? So in particular, for instance, so we're going to have some omega, okay, omega mu, if you wish, which is going to be integral d3x of the omega mu. Then we'll see which index mu survives in this thing, right? So we integrate everything. The integral of the Lagrangian density is going to be the Lagrangian. The integral of this omega is going to be what I call omega hat mu. Okay, so now derivative. I said that, all the derivatives with respect to space disappear from the game. So therefore in here, I'm only going to have derivative with respect to time. Derivative with respect to space disappears. There is no space as an index, right? And then derivative with respect to the fields. After I integrate, this is going to be the derivative of the Lagrangian, not the Lagrangian density, because I'm integrating over dx, with respect to the fields. And the only component that is left is time. So that means derivative with respect to q dot I, if I have more than one, okay? Variation of that. So variation of that minus, okay? Now here, what I'm going to have here. So I have minus, and minus gives me plus. So let's look at this term first. So this is going to be, I'm sorry, no, I'm looking at this term first. So that means that the mu is 0. That means nu has to be 0 as well, because otherwise this term is not there. And then I integrate, so that means L, right? So mu is 0, because time is the only thing that survives in this derivative. And then nu has to be 0 as well. So that's L minus, this is this minus, integral dl, that's again derivative of the Lagrangian, with respect to derivatives of the field. So that's derivatives of the variable times the same thing, because mu and nu are the same, right? Mu and nu are the same. That's the only thing that can survive here. I cannot take derivative with respect to space. Nu has to be time as well. It's the only thing I can take derivatives of. Okay, so this means q dot. Okay, variation of x. Well, the variation of x, it's only the variation of time. There is no space variation. So that's variation of time plus this omega hat equals 0. And indeed, that's exactly, Noether's theorem for discrete systems. So this is Noether's theorem for discrete systems. For systems with a finite number of degrees of freedom. So you see that the Noether's theorem, the version of Noether's theorem that we derived, is actually a generalization. It also encompasses this case for discrete systems as a particular example. Any questions about this before I move to an example in which we start with a Lagrangian, compute equations of motion, and also compute, the associated Noether's theorem associated to a certain symmetry. Just one example. So any questions or comments? Yes or no?
No.
Okay. So let us look at this example. So the example is given by the following Lagrangian density, which is going to be a function of the real part and the imaginary part of a complex field. So that's real and imaginary are independent. So I can also talk about the field and its complex conjugate, right? So instead of the real part and the imaginary part, I can talk about the field and its complex conjugate. So psi and psi star are independent. Independent fields. Psi and psi star fields. And the Lagrangian is explicitly given by this expression. I psi star derivative with respect to time of psi minus 1 over 2m. And this is gradient of psi star dot gradient of psi minus a certain function of x times psi star psi. Okay, and this x could be, x in here could be space and time, everything, if you wish. Okay, so whatever. Although the most normal situation is that this only depends on space. It does not depend on time, but it could also depend on time. So the first thing that we want to do with this Lagrangian is derive the equations of motion. Euler-Lagrange equations of motion. And if you remember the Euler-Lagrange equations of motion, they look like dl d psi minus d mu dl d psi comma mu equals 0. That's for psi. And for psi star, the same thing. Psi star minus d mu dl d psi star comma mu equals 0. Okay? Equals 0. So let's compute this thing. Okay, so let's start with psi star, and then we'll do the same thing with psi. So let's take the derivative of L with respect to psi star. So how much is this? Who can tell me? What is the derivative of L with respect to psi star?
I time derivative of psi.
Yes.
Minus Vx psi.
B of x psi. Okay. And now, what is the derivative of L with respect to psi star mu? Well, I mean, here we have to distinguish, right? So it's a good idea to distinguish. So let's write this thing as 0 equals partial of L with respect to psi star minus time derivative partial of L with respect to psi star 0. So that's the time derivative minus derivative with respect to the spatial components dl with respect to psi star spatial derivative with respect to spatial components, right? So let's do it step by step. But since this is the first time that we do it, let's do it step by step. So what's the derivative of L with respect to the time derivative of psi star? I'm looking for the first term. No.
0.
Is 0. Yes, it's 0 because there is no time dependence of psi star anywhere. So that is 0. Okay. Now, what is the derivative of L with respect to psi star, comma I? So that means the derivative with respect to the derivative of L with respect to the derivatives, the special derivatives of psi star. How much is this?
Minus 1 over 2m, the gradient of psi.
Gradient of psi. This cannot be right because this is a vector and this is something that has an index. So it's almost right, but we have to be a little bit more careful.
Psi I?
Yes, psi comma I if you wish. Or derivative I of psi, because this thing here, let me write it here. This thing here is the same as di psi star di psi, right? I mean, look at this thing. This thing is just, you know, something that is not relativistic at all, right? So this is just the derivative with respect to x times the derivative with respect to x, plus the derivative with respect to y times the derivative with respect to y, etc., etc., etc. So I don't have to worry about anything, right? It's just, you know, the sum of the three derivatives with respect to x, x, y, y, and z, z. So this is like this, okay? And so if I now take the derivative, you know, here I have to take the, you know, derivative respect to xi of this thing. So this is the derivative respect to xi of this thing. This is going to be the derivative respect to xi of this thing. So this is going to be derivative with respect to xi of the derivative with respect to xi of psi, right? So this is minus 1 over 2m. Now I'm summing, so this is Laplacian, right? So this is the Laplacian. You guys agree with this?
Yes.
Yes.
Okay, so now with the three pieces together, this and this and this, we already have Euler's Lagrange equation. So that means that 0 equals I dt psi minus v of x psi, that's this guy, minus the time derivative, this guy is not there, minus, and minus is plus, 1 over 2m Laplacian of psi, okay? So this equation, I can also write as I dt psi, and then I pull this guy and this guy to the other side. So it is minus 1 over 2m Laplacian of psi plus v of x times psi. So this is an old friend, right? So whose equation is this?
Is similar to Schrödinger equation.
Similar or not, it's identical. It's totally identical, right? That's a Schrödinger equation.
Each bar equals 1. No?
Okay. The Schrödinger equation. Yes, absolutely. So this is h bar equals 1 equals c. C doesn't play any role here, but yes, you are right. There should be an h bar. So this is in the units in which h bar is 1, but it's a Schrödinger's equation. Exactly Schrödinger's equation. So if you wanted to have an h bar and then to be happy, then you would have to multiply h bars here and here. So an h bar here, an h bar square here, and then it will be exactly the same. So this is in these units, okay? Now, so this is interesting, right? Because now it looks as if we have a classical field equation, classical field theory, which is equivalent to Schrödinger's equation, right? At least for psi. And now, of course, this was only one of the two equations because we have two fields, psi and psi star. And we only computed, the Euler-Lagrange equation psi star. We took just derivative with respect to psi star everywhere, and we got this. Now we could do the same thing for psi. So we can compute derivative of L with respect to psi. Now let's repeat all this thing, but now for the other field. We have two fields, we have to do it for both. So what's the derivative of L with respect to psi? Tell me.
Minus v of x, psi star.
Yes, minus v of x, psi star. So that's the first guy. Now there is no derivative with respect to time here. So before there was one because I was taking derivative with respect to psi star, but now the only piece is this one here that I have to look at for this derivative. Let's go on. Okay, now we have to take the derivative with respect to time. We are looking for this thing for psi now. Okay, so what is the derivative of L with respect to psi, comma 0? So that's the derivative of L with respect to the time derivative of psi. So how much is this?
I psi dot
I psi
star.
star. I psi star, yes. Okay, and now the derivative of to psi, comma I, as before. Right, so how much is this?
Minus 1 over 2m of the Laplacian of...
No Laplacian. There is an index here.
Di psi.
Okay, di psi, yeah.
Di psi
Psi star.
star. Yes. Okay. And now we have to write derivative of L with respect to psi. I'm copying this equation minus derivative with respect to time of the derivative of L with respect to psi comma 0 minus derivative I of the derivative of L with respect to psi comma I, and this has to be 0. Okay, so let's write all these terms because we already computed them. Okay, so this is minus, so the first guy is minus v of x psi star minus dt of the derivative of L with respect to psi 0, which is this I psi star minus derivative with respect to I of this guy. So let me just write minus, and minus gives me a plus 1 over 2m, and then derivative I with respect to this thing. So that's derivative I of the derivative I of psi star. So before we got this equation, and now we have this other equation, which says, let me just pull to the left-hand side this guy. So that's I derivative with respect to time of psi star. I'm pulling this guy to the left-hand side. And this equals 1 over 2m. Now, this is the Laplacian now, right? This is the Laplacian of psi star minus this minus here, v of x psi star. Okay? So now I can multiply the whole equation by minus 1. So then I have minus here, plus here, minus here. And I find another equation. So what equation is this one?
Is the complex conjugate of the Schrödinger equation?
Absolutely. Complex conjugate of the previous Schrödinger's equation. Exactly. So it's not a different equation. It's the same, but for the complex conjugate. You just complex conjugate this thing, and you get this thing. Aha. So that means that this Lagrangian here is nothing but, you know, a field theory version, classical field theory version of quantum mechanics. Okay, so that's interesting. That means that quantum mechanics could be formulated in terms of field theory. The only thing that we are not doing yet is we're not quantizing this thing, but we could quantize it. We could quantize this theory that you guys will do in the second semester, right? Those of you who are interested. So those of you who are interested could quantize this theory, and the quantum version of this theory would be equivalent to quantum mechanics. Okay? Now, we can also do other things. So let's write down the Lagrangian again, and we'll look at it. Okay, so this is I psi star time derivative of psi minus 1 over 2m gradient of psi star dot gradient of psi minus v of x psi star psi. Okay, the same Lagrangian. Now, we see that this Lagrangian is clearly invariant under the following transformation: e to the I epsilon times psi. And if we make this transformation for psi, of course, we're making this transformation for psi bar. And if we do this, the Lagrangian is completely invariant, clearly, right? Because I multiply this guy by e to the minus I epsilon. I multiply this guy by e to the plus I epsilon. So epsilon, I'm going to take it to be real and constant. So this guy here, you know, it remains invariant after I make this transformation. And this guy also remains invariant after I do this transformation. The epsilons cancel out, and this guy also. So this whole thing is a symmetry. So this is a symmetry transformation, clearly. Is a symmetry transformation. And since it's a symmetry transformation, Noether says there has to be a conservation. Right? So this is Noether's theorem. Noether's theorem says there has to be a conservation. So who is going to be the conserved quantity? Well, okay. So the first thing that we have to figure out is we have to make this transformation infinitesimal. But that's very simple, because that means that psi goes to 1 plus I epsilon plus dot 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 times psi. So that means it's psi plus I epsilon psi plus order epsilon square. Remember that for Noether's theorem, we can drop order epsilon square terms. And psi star is going to be 1 minus I epsilon plus dot 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 psi star. So this is psi star minus I epsilon psi star plus order epsilon square. So this means that delta psi, so the variation of psi is I epsilon psi, has the epsilon, and delta psi star, so the variation of psi star is minus the same thing with a psi star. Okay, so this is a minus sign. Okay, now we just have to go and look at the expression of Noether's theorem. Noether's theorem says that d mu j mu, and since this Lagrangian here does not, it has this dependence on explicitly on x, so I have to keep this thing. Okay, so d mu j mu equals 0, where j mu is the derivative of L with respect to all the fields eta rho comma mu delta eta rho plus nothing, because this other thing had a delta x mu, and there is no delta x is not changed. I'm only changing the fields. I'm not changing space or time. So this term is not there. And also there is no omega mu, right? Because when I make the transformation, the Lagrangian stays the same. Doesn't pick an extra term. Doesn't pick a d mu omega mu or anything. So that's it. That's all there is. So now I have to compute this thing where eta rho is psi and psi star. These are the two fields that I have. Okay. So who is J0? We compute J0, we compute Ji, and then we just do this calculation. So who is J0? So J0 is the derivative of L respect to psi comma 0 delta psi plus dl with respect to psi star comma 0 delta psi star, right? I'm summing over rho, so that means I have to sum all the fields that I have. I have two fields in this case, psi and psi star. You guys agree?
Yes.
Okay, so let's compute each term. Who is dl, the derivative of L with respect to psi dot 0? Psi comma 0, I mean. This guy first. How much is this?
I psi star.
I psi star times delta psi plus, who is the derivative of L with respect to psi star comma 0?
0.
Nothing. Yes, 0. So that means it's I psi star delta psi, but delta psi is I epsilon psi. So I and I gives me a minus epsilon psi star psi. Right? That's what I get. I and I is minus epsilon psi star psi. So that's J0. And now let's compute Ji. So who is Ji? So this is the derivative of L with respect to psi comma I delta psi plus derivative of L with respect to psi star comma I delta psi star. Okay? So who is the derivative of L with respect to psi comma I?
Minus 1 over 2m di psi star.
Yes, di psi star. And now delta psi. Okay, so delta psi. Plus, same thing now with respect to psi star. So we repeat the same thing now. But we exchange the roles of psi star and psi. So this is di psi times delta psi star. Okay, so let's write what this is. So delta psi is I epsilon, right? So this is minus I epsilon divided by 2m. And then we have psi, derivative I of psi star. And then here we have delta psi star, which is minus and minus gives me a plus I epsilon divided by 2m. And then we have psi star di psi. Okay, so that's what we have. All right, so this we can write as I epsilon divided by 2m. And then we can write psi star di psi minus psi di psi star. Right? So if I pull out this guy, you have psi star di psi minus psi di psi star. Okay, so now we have to compound this thing. Just do time derivative of J0 plus a special derivative of Ji. So let's do this. So what is the time derivative of J0? And who is J0? Is minus epsilon psi star psi. Minus epsilon psi star psi. Now plus special derivative, so plus derivative respect to I of this other thing, which is I epsilon over 2m, I epsilon over 2m. So let me just write it like this. And let me just pull the derivative past this guy. Acting on this combination. Psi star di psi minus psi di psi star. So that's psi star di psi minus psi di psi star. And this whole thing has to be 0 because that's the d mu, sorry, that is the d mu j mu of Noether's current, okay? Now, this whole thing is 0, does not depend on epsilon, which is a constant. So I can divide by epsilon. Epsilon should not appear here at all. And what I find is, I find that I multiply everything by minus 1. So d dt of psi star psi minus, because I'm multiplying everything by minus 1, I over 2m. And this is going to be the gradient of psi star, sorry, the divergence of this vector minus psi, this thing, equals 0, okay? All right, which I can also write in a different way, like d dt psi star psi, and then I put a plus sign here, 1 over 2m, and this is going to be nabla acting on this thing, but now I have to put this guy first. So this is psi gradient of psi star minus psi star gradient of psi equals 0. Now, who recognizes this equation now? What is this equation?
Continuity equation.
Absolutely. So this is the continuity equation. Continuity equation, which is the conservation of probability. Conservation of probability, where rho, now this thing we can write as d dt of rho plus divergence of j equals 0, where rho equals star psi is the probability density, right? Probability density in quantum mechanics. So as you can see, you recover, this conservation law as a consequence of a symmetry. Now it's a symmetry. This symmetry is responsible for that. So it's just another example how a conservation law, is the result of a symmetry. Now, in field theory, and actually in quantum field theory, rho equals psi star psi is no longer the probability density, but you multiply the whole thing by the electric charge, okay? And this is the electric charge density. So this is the thing that I cannot explain why that has to be so, okay? But in quantum field theory, this function psi is no longer the wave function, okay? It's another thing. It becomes a quantum operator, becomes an operator. And this equation, is reinterpreted as the conservation of electric charge, just by multiplying everything by the electric charge of that field. But as you can see, the structure is exactly the same structure as in quantum mechanics, as is Schrodinger's theory. Okay. Okay, good. So that was only an example. Any questions? In quantum mechanics, in quantum mechanics. In quantum field theory. In quantum field theory. Okay. So any questions or comments?
No questions.
Okay. So now we have done enough about the Lagrangian formulation of field theory, but you guys already know that for discrete systems, there is an equivalent formulation, which is Hamiltonian formulation of discrete systems. So there has to be a Hamiltonian formulation of field theory, okay? So that's the thing that we're going to discuss now. Hamilton formulation of field theory, of classical field theory. Okay, well, the reason why we do this is not only completeness, right? It's not only the fact that, yeah, so since we know that there is a Hamilton formulation which is equivalent, let's do it again. The reason why we do this is because Hamilton's formulation will allow us to define what we understand by canonically conjugate momentum, right? So this will lead to something we will call canonical conjugate momentum. And this is something we need for quantization, right? For quantization. Because we know that we have to take Q and P, right? And write this as, let me just do it the other way. The commutator of Q and P operators is I H bar, the Poisson bracket. So this is the Poisson bracket, Poisson bracket. So we need this. We need this canonically conjugate momentum P, and that goes through the Hamilton's formulation. So we have to have some Hamilton's formulation. Now Hamilton's formulation, Therefore, it's necessary to quantize, at least in this standard way, with the commutator, with this, this rule. It has the disadvantage that Hamilton's formulation is not explicitly relativistically covariant. So in a relativistic theory, and we know that nature is relativistic. In a relativistic theory, so we need to talk about the relativistic theories. In a relativistic theory, Hamilton's formulation is not the easiest one because it separates time from the rest, okay? Whereas in relativity, time is just another coordinate, just as space is. So it's not explicitly relativistically covariant and makes your relativistic formulation a little harder. But the fact that it's not explicitly relativistically covariant doesn't mean it's not relativistically covariant. And therefore, you can also formulate the relativistic theory in Hamilton's formulation. It's only that you have to work a little harder. So that you will see, in detail, again, when you quantize the theory. But so far, we're just going to do it as if, we are forgetting about this fact. So this is, the underlying reason why Hamilton's formulation is interesting. Mainly the first one. And the second one is an extra complication that one has to deal with. Okay, so let's see how we formulate this Hamilton formulation for classical field theory. Okay, and the way to do this is we go back to the discretized version. Discretized version of a continuous system. Continuous system, which in our case, remember, it was the string or a rod, or, that's the way we started, right? The formulation of classical field theory. We just went back to, an infinite string of little particles with mass m, and we were taking the continuous limit, right? And so if you go back there, you will see that we had something called the Lagrangian, which was the sum over I of A, which was the distance between the two masses, times an expression that we called Li for each and every one of those masses, and this was 1/2 of the sum over I of A times, and this is now this Li, so this is m over A, and we had q dot I squared minus Ka, which was Young's modulus, if you remember, Qi plus 1 minus Qi divided by A, whole thing squared. So this was the Lagrangian of our system, right? So this was the system in which we had a spring, a mass, a spring, a mass, spring, a mass, spring, etc., etc. And the mass of this guy was m, A was this distance, and so on and so forth, right? And we wanted to take the limit, A goes to 0. A goes to 0. Okay, so we want to take the limit, A goes to 0, in an intelligent way. We cannot just do it like this. In particularly, we wanted to take the limit A goes to 0 with one constraint, which now is going to be important. Limit A goes to 0, but with m over A equals constant, right? Because this was the mass density, the mass per unit length. So this was constant, and this is something we called mu at the time, mu at the time. Okay, now, so let's do this. Now we have a Lagrangian. From a Lagrangian in a discretized version, at least we know how to compute the momentum, right? The canonical conjugate momentum. So let's define the canonical conjugate momentum Pi as for a discrete system, derivative of Li with respect to Q dot I, right? That's the naive thing that we could do. But when we do this derivative on this expression, on this Lagrangian here, of course, we have the distance between the two masses, the derivative of one of these summands with respect to Q dot I. And this is A times M over A times Q dot I. That's what I find. If I take the derivative with respect to Q dot I get A times M over A times Q dot I. That's what I get. And what I see is that if I define the canonically conjugate momentum like this thing, when A goes to 0, M over A is mu a constant, disappears, goes to 0. So this definition is no good. I cannot define a P canonical conjugate momentum like this because this is going to disappear in the continuum. So this is not a good definition. So we have to define something else. And it's clear what we have to do. What will make sense is to define the canonically conjugate momentum per unit of length. If I divide by A, then the whole thing is going to work. So yes, so this is what we do. So we defined the canonical conjugate momentum density. So as in with other things in field theory, there's a Lagrangian density. So now there's going to be a canonical conjugate momentum density, and we call this thing pi. It's a little bit unfortunate that it's called pi as the number pi, but that's almost everybody does this thing. So I'm also going to stick to this nomenclature. So this pi is going to be the limit when A goes to 0 of pi divided by A. And this is going to make sense because this is the limit when A goes to 0 of M over A times Qi. Okay, and this you can check that is the same as the derivative of the Lagrangian density with respect to Q dot of X. Okay, because if you remember each and every one of these LIs in the limit when A goes to 0 is what we call the Lagrangian density, right? Because remember that the whole Lagrangian is the sum over I of A Li. So that's the thing that I had before. Okay, and this goes in the limit A goes to 0 integral dx of the Lagrangian density. So this now is going to make sense. So we are talking about densities in both sides. So this is density of canonical conjugate momentum, and this is the density of the Lagrangian density. So that's the thing that I have to take the derivative, of with respect to Q dot. And this Lagrangian for this system, remember, it was 1/2 of mu, this mass density, times derivative of Q with respect to T squared minus Young modulus derivative of Q with respect to M squared. All right, so this was the Lagrangian density of that system. So now we can compute this pi. Okay, so who is pi? So pi of X is the derivative of this L with respect to Q dot. So that is mu Q dot of X, right? So that's what it is. That's what it is. Okay, so now that we know how to compute the canonical conjugate momentum, we can compute the Hamiltonian. What is the Hamiltonian? In the discrete version is the limit, is the sum of pi times Q dot I minus the Lagrangian. All right, but this is the sum over I of A times the derivative of Li with respect to Q dot I. I'm just using this definition here. So Pi here is this object. So for instance, I could just write it like this, right? So this Pi here is A times derivative of Li with respect to Q dot I, like here. So this is what I'm writing, times Q dot I minus L, And this is the same, I pull out an A. So the sum over I of the derivative of Li with respect to Q dot I times Q dot I minus Li. And so this, when A goes to 0, has already a well-defined limit, right? Because it's going to be the integral over x, okay? Sum times A is the integral over x of this object here becomes the derivative of L with respect to Q dot x times Q dot x minus the Lagrangian density. And this we can define as integral over x of the Hamiltonian density. So this is now going to be the Hamiltonian density. Hamiltonian density that, as always for a Hamiltonian, we're going to consider a function of Q of x and t, pi of x and t, and if necessary, derivatives of Q and derivatives of pi if I have them, okay? But definitely no Q dots, okay? No Q dots, because the Q dot is, is to be used inverted here in terms of pi, as in the case of the Hamiltonian, just as in the case of the Hamiltonian. So from pi of x and t equals derivative of L with respect to Q dot x and t, which is going to be a function of Q dot of x and t, Q of x and t, and maybe also derivatives with respect to x and t, special derivatives, right? One has to invert this to obtain that Q dot of x and t is a function of pi of x and t, Q of x and t, and if there are also special derivatives of Q of x and t. So if Q dot cannot appear in the Hamiltonian, that we already know. We have done, we have insisted on this many times for a discrete system. Now it's exactly the same story, but now for the Hamiltonian density H, this H here. So the same way we were talking about the Lagrangian density L, now we're talking about Hamiltonian density H. Okay, exactly the same. And now we're going to generalize it to 3 special dimensions and blah, 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 blah. Okay, and we have to derive Hamilton's equations for this. Okay. Now, any questions? Or comments? I'm going to
no questions.
I'm going to change the color of this thing so that you can see it better. Okay, so this goes to A. This goes to A derivative of Li with respect to Q dot I. Okay, so if there are no questions or comments, then we're going to leave it at this point. And then the next day, we're going to derive Hamilton's equations. And we have to check that Hamilton's equations are, equivalent to Lagrange's equations, Euler Lagrange's equations, and so on. Okay, so that's enough for today. All right, thank you.